Imagine you have trained an AI on your company's knowledge base. Product documentation, internal policies, support articles, and customer information. Now, a user asks your chatbot a question and expects an answer almost instantly. The challenge is that AI doesn't work with the text the same way the humans do, as we already know from our previous lessons. Before it can search through information, it converts every document into a vector, which is a long list of numbers, and captures the meaning of this text. The numerical representation is called embedding. For example, a document that returns policies becomes one vector. A document about shipping becomes another vector. And after processing thousands of documents, your entire knowledge base turns into a huge collection of vectors. When a user asks a question, the question is also converted into a vector. The AI then needs to find the documents those vectors are most similar to the question's vector. In other words, it isn't searching for matching keywords, it is searching for similar meaning. Without a specialized approach, the system would have to compare the user's vector against every vector in the database one by one. And as your data grows to millions of documents, that quickly becomes too slow for a real-time application. And that's exactly the problem vector databases were created to solve. So, a vector database is a specialized engine built for one specific task: find similar vectors quickly. With a traditional database, you usually ask questions like, find this exact record, or show me all rows that match these conditions. A vector database works differently. Instead, the question is, which vectors are more similar to this one? A helpful way to think about it is to imagine two librarians. The first librarian only works with the exact information. If you ask for a specific book title, they will find it immediately. But if you say them something like, I am looking for a story about ambition, success, and the cost of chasing wealth, they don't know what to do. They need exact matches. The second librarian understands meanings. You describe the idea, a topic, or even a feeling, and they immediately know which books are related. They understand that different words can point to the same underlying concept. A vector database works like that second librarian basically. Because the information is stored as vectors, similar ideas end up close to each other in vector space. When a user submits a query, the database looks for nearby vectors and returns the most relevant results. This is what makes semantic search possible. Imagine someone search for Italian restaurants. A traditional keyword search might only find documents that contains those exact words. A vector database can also find content that talks about something like homemade pasta or authentic Italian cuisine, because it recognized that these ideas are closely related even then the wording is different. The main idea behind vector databases is something called Approximate nearest neighbor search. Approximate here is important. It means we don't try to compare everything perfectly, because that would be too slow at scale. Instead, many systems use the algorithm like hierarchical, navigable, small world. You can think of it like a map with layers. And the top layer, you only have a few reference points that are the far apart. Below that, there are more points. At the bottom, you have all your vectors grouped so that similar ones stay close together. The structure is built once then you upload your data. After that it stays ready for fast search. When a user asks a question, the system doesn't check every vector. It starts from the point in the structure and quickly moves toward the closest matches step by step. It is like searching for a place using shortcuts instead of checking every house on every street. In milliseconds, the system finds the closest vector to your question. To measure similarity, it usually uses things like cosine similarity, which checks how close two vectors are in meanings. The key point is simple here: even with millions of vectors, search stays fast. Scale completely changes how vector databases behave. If you have under 1 million vectors, almost any tool works fine. You won't feel big performance difference yet. From 10 million to 100 million vectors, things get more serious. Now speed matters a lot. You want results in under 100 milliseconds, but not in seconds. At this point, choosing the right tool starts to matter. At 100 million vectors and above, you need serious infrastructure, often distributed systems or highly optimized engines. The main idea here is that you have to think about the scale on the early stages, because it is much harder to migrate later. So now let's consider a very short, very high level review of some of the tools for the vector engines presenting in the market. We are going to dive deep into some of them in the next videos. But for now the goal is simple. I just want you to know that these tools exist in a high level and to understand which type of tool might be a good starting point for your specific situation. So instead of trying to master everything right away, focus on the big picture first, understand what each tool is generally used for, and then later go deeper when you actually need it. So, the first one we are considered to talk about is the Pinecone. It is a fully managed system. You don't need to worry about the services and scaling. You just use it from the box. It is easy and reliable, but you don't control the infrastructure. The second one is the Weaviate, which is the open source and flexible. You can run it yourself and use it in the cloud, and it gives you more control and customization. Qdrant is also open source and very fast. It is lightweight, written in Rust, and good for production system with good performance. pgvector is an extension for the PostgreSQL. So if you already use Postgres, this is the simplest way to add the vector search without adding in a new database. And the Chroma, which is very simple and great for learning or prototypes, not designed for the huge scale, but perfect for getting started. So the simple way of choosing would be, if you need to prototype something, you may take Chroma first. If you need something managed production, you can take Pinecone. If you need open source plus a bit of control, so Qdrant is your choice, or you may try Weaviate. If you already use Postgres, then pgvector is your choice. Here I would say that an important thing would be just to pick something at start and don't overthink it at the very beginning. So, vector search is great at meaning, but it struggles with the exact values. For example, imagine a user searches for a product code like FX47Blue. Vector search understands meanings, not exact IDs, so it might return similar blue products, but not the exact one. And that is the problem. The hybrid search solves this by combining two methods. The vector search finds similar meanings. The keyword search finds exact matches. They run together and results are combined. So if someone searches blue wool sweater, the system shows both exact keyword matches and similar items like navy knit sweater. This makes search much more reliable in a real product. So let's talk about embeddings versus vector databases. People often mix this up, but they are two different things. An embedding model takes text and turns it into numbers in vectors. That's all it does. A vector database stores those vectors and finds the most similar ones. So, embedding model creates vectors. Vector database searches vectors. They work together, but they are separate tools. For example, you can use OpenAI embeddings with Pinecone or Cohere embeddings with the Qdrant. A big mistake is trusting benchmarks too much. The real-world data is messy and results can be very different from test datasets. Always test with your own data. Another mistake is over-focusing on internal details and tunings. In most cases, what matters more is good embeddings, clean data, and proper evaluation of results. Also, many people think that the job is done after choosing a vector database, but it is not. You still need monitoring, update, and maintenance over the time. All of this mentioned above is used in something called RAG, which is Retrieval Augment Generation. RAG lets AI answer questions using your own private data, and we will spend some time in the next videos explaining and building some of those RAGs. But here on the top level, I just want you to know that the information we are going step by step are already pass us to the very important and advanced field. So, how the basically RAG works? Your documents are turned into embeddings. They are stored in a vectored database. A user asks a question, the system retrieves relevant documents, and the AI uses them to generate an answer based on your data. So, for example, customer support bots, internal company assistants, knowledge base, AI tools, all could be built and based on RAG. And every of them could be too slow without the fast vector search. Think of vector database like this. If your problem is about meaning and similarity, vector search helps. If your problem is about exact matches, you also need keyword search or hybrid search. Vector databases are not magic, they are just a tool for semantic search. But they are now a key part of the modern AI systems. If you are building anything with AI today, understanding them is no longer optional. If you found this video helpful, learned something new, or discovered ways to simplify your workflow, boost your productivity, or even save money, please subscribe my channel and hit the like, because it really helps me to grow and keep digging to discover new things and continue creating more content like this. Also, leave a comment below with your thoughts, questions and experiences. My goal is for us to learn, grow and build real AI expertise together, and your feedback is an important part of that. Thanks for watching and see you in the next videos. Laughing, dance all night.